in a previous session, you looked at some basic motional EMF, right? This was much prior to this concept of motional EMF existed much prior to those monumental experiments that Faraday performed in 1831. So motional EMF was essentially, magnetic forces acting on charges, causing charge separation, producing an EMF, driving a current if there was a loop, and so on and so forth, right? It was a magnetic force that produced an electric field. The electric field resulted in an EMF, right? Now, 1831, Faraday performed a series of 3 experiments. Those were met with tremendous amount of violence in the community of physicists. Much of it looked like an accident, and people were unwilling to digest the results of the 3 experiments that Faraday performed in 1831. What he did was, took a magnet, experiment number 1. He took a magnet, so there was a magnetic field associated with it. There was a magnetic region of magnetic field produced, let's say, by a magnet. Okay. And this was a loop. This was a loop, PQRS. The magnet was kept stationary. Whereas the loop was given a velocity v to the right. Loop moving, magnet stationary. This was experiment 1. The magnet was kept stationary and the loop was moved to the right with a velocity v. And he found that there was a current that was driven through the loop. There was a current I driven through the loop. That was experiment 1. Now, experiment 2. This was the magnet. This was the loop. And this time, the loop was kept stationary and the magnet was moved to the left with a velocity v. That was experiment 2. Magnet stationary. Magnet moving and loop stationary. Magnet moving and loop stationary. The magnet was moved with a velocity v in this direction and the loop was kept stationary. And he found that the same current I was driven through the loop. Found that the same current I was driven through the loop. That was experiment 2. Experiment 3. He maintained both the loop and the magnet stationary. Both the loop and the magnet were maintained stationary. Both stationary. But the magnetic field here was intensified. This could have been, say, an electromagnet. Driving more current through it would give rise to a higher value of the magnetic field. Magnetic field intensified. And there was a current I then again found to be driven through the loop. Now, experiment 1 was an established fact well prior to Faraday, because experiment 1 was really an instance of motional EMF. See, PQ was a conductor. PQ was a conductor moving past a magnetic field. A conductor moving past a magnetic field. It had a velocity v to the right. B was into the plane of the board. So V cross B was towards Q. So positive charges accumulated at Q, negative charges at P. There was a clockwise EMF generated that generated a clockwise current through the loop. Right? Isn't it? So that was experiment 1. And there was no debate on this. This was known to physicists for a long time. Right? So the motional EMF aspect was could explain why a current was driven through the loop when the loop was moved to the right. Right? Essentially, a current is obtained if there is an electric field which generates an EMF and so on and so forth. Now, in 2, the conductor moving past the magnetic field PQ, the conductor in the magnetic field PQ was stationary. So it didn't experience a magnetic force. It didn't experience a magnetic force. If it didn't experience a magnetic force, there was still a current, there was still an EMF. That means there must still have been an electric field generated inside the loop, which generated an EMF that could drive the current through the loop. Right? That was experiment 2, which could not explain, based on motional EMF, how the current I was driven through the loop. Because there was no force acting on charges at rest. The conductor PQ was charges at rest. Therefore, they didn't experience a force, a magnetic force, which could create an EMF, which could generate a current through the loop, right? So this was an issue. This was an issue with this loop. None of the facts known until then in physics could explain this, right? None of the facts known in physics could explain this. Experiment 3, once again. The conductor was at rest. Yet there was an electric field generated, yet there was an EMF that could drive the current through the loop, right? Again, a fact which did not have enough rationale by then, right? So 2 and 3 in that context, belong to a common framework. 1 was a straightforward instance of motional EMF, and everything could be explained as far as 1 was concerned. Now, physicists, in fact, at that point of time, termed 1 and 2 as a peculiar accident. They looked upon 1 and 2 as a peculiar accident, where they said, well, there could be nothing authentic about this happening. It's just an accident or a mistake that has been made. That means, whether the loop moves with a velocity v to the right or the magnet moves with a velocity v to the right, the fact that it drives the same current through the loop is an accident. That's what they looked at it as. Much later, much later, when Einstein came up with his theory of relativity, it got very well understood. These Faradays laws got very well understood in the sense that it was not the velocity of the loop or the velocity of the magnet. It was the relative velocity between them which mattered. But then, that was the foundation stone of the special theory of relativity. And Faraday knew nothing of relativity. Faraday really didn't know anything of relativity. But then, it was not explained by any known principle in physics, why 2 happened, right? Now, the genius of Faraday, the ingenious of Faraday, then said, well, every time there was a change in flux associated with the loop, there would be an EMF generated. Whatever be the reason, whatever be the cause, whatever be the reason, whatever be the cause, if there is change of flux associated with the loop, there would be an EMF generated in the loop which would drive a current through the loop. This is what he pronounced. a common mathematics, obviously the physics associated with this and the physics associated with this was different. It's not the same physics. Yet a common mathematical framework. He said, well, flux, of course, like electric flux, there is a magnetic flux, right, which would be B dot dA. Exactly the same way like we calculated electric flux, B dot dA. So then he said, well, if phi is the flux associated with the loop, then d phi dt, rate of change of flux with time associated with the loop, will measure the EMF generated in the loop. And this EMF is called induced EMF. This EMF is called induced EMF, and it's written as minus d phi dt. Again, I have some very special and adverse remarks about this minus sign, but we'll come to those adverse comments about this minus sign later on. But for the time being, the induced EMF, the EMF induced in the loop, would be minus d phi dt, rate of change of flux with time associated with the loop. He said, whatever be the cause, be it motional EMF or something else, the effect is actually this. The induced EMF would be minus d phi dt. Minus is supposed to give you the sign of the induced EMF, and I say bullshit. This will never give you the sign of the induced EMF. Minus, I do not know how it came down, from one person to another through generations, from one book to another, from one author to another. But down the line, I'll establish that this minus sign is incapable of giving you the direction of the induced EMF, clockwise or anti-clockwise. But this minus sign purportedly is about giving you the direction of the induced EMF. It never does so, really. But nevertheless, in an examination, you might always want to put a minus sign and say minus sign gives us the direction of the induced EMF. Finish. But for the sake of the class, when we solve problems, you'll realize I put a minus sign and there is no possibility that you'll be able to give me the direction of the induced EMF with the minus sign being there or not being there. In the context of genuine problem solving, we would look upon the induced EMF as magnitude of d phi dt, and then we'll determine the direction of the induced EMF from independent considerations. All right. We will give no respect to this minus sign when we solve problems. Of course, this set of experiments might have actually inspired Einstein to come up with a special theory of relativity, which very closely connected all of electricity and magnetism. It was a union of electricity and magnetism. They feel that, this was the inspiration for special theory of relativity. Now, as far as the direction of the induced EMF is concerned, see, this is the magnitude of the induced EMF, d phi dt. Now, as far as the direction of the induced EMF is concerned, it comes out of a cardinal statement made by Professor Lenz, and he pronounced this as Lenz's law. It said, one single statement, one single line. He said, nature abhors change of flux. Nature abhors. Abhors means hates change of flux. Nature abhors change of flux. Eventually, in each of these cases, there must have been an electric field and EMF. Now, whatever be the physics behind the generation of the electric fields and EMF, this is the mathematics of the same, right? The induced EMF, no matter what the cause is, no matter how it happens, it's going to be negative of the rate of change of flux associated with the loop with time. Now, nature hates change of flux. This then becomes cardinal towards establishing the sense of the induced EMF clockwise, anti-clockwise, one way or the other. In this case, for example, realize that when I move it to the right, this portion of the loop has flux associated with it, magnetic flux associated with it, right? Which decreases, right? the direction of the induced EMF would be such to frustrate this, so as to frustrate this, so as to mitigate this effect. That means the number of field lines going into the plane of the board through the loop would decrease, direction of the induced EMF and therefore the direction of the induced current, this is the induced current, would be such so as to augment more field lines going into the plane of the board, so that partially the loss of field lines going into the plane of the board is compensated. You know what I'm saying? When this moves to the right, the total flux associated with this loop will decrease, because this portion, this area is decreasing, right? So the total flux associated with the loop is going to decrease, which means the direction of the induced EMF and the direction of the induced current would be such so as to oppose this. If the current were to be driven like this, in a clockwise sense, realize that there would be more field, because of this induced current, there would be more field lines going into the board, which would, although to a very, very small extent, negate the loss of flux going into the plane of the board. It would augment more field lines going into the plane of the board, very partially negating the effect of loss of flux because of the rightward movement. But then that's good enough for us to understand why it's going to be clockwise in this case. Right? Yes or no? So the direction of the induced EMF will always be such so as to oppose the very cause towards which it is, for which it is due. That's the basic idea. The minus sign here is no good. You would have to physically examine the direction of the induced EMF, that is the direction of the induced current, one way or the other, to know whether it's going to be clockwise or anti-clockwise in one way or the other. What would frustrate the change of flux? The effect that would frustrate change of flux would give us the direction of the induced EMF, the direction of the induced current. Yes or no? You know what I'm saying? Now, again, you know, this entire thing was referred to as Faraday's Law. In my view, you know, all these belong to a common mathematical framework, but the physics is not the same. One, of course, belongs to one kind of framework. 2 and 3 belong to another family. And to call them by the same name, Faraday's Law, to me, it seems being a little insensitive towards the subject, because a common mathematics, but entirely different physics associated with the two effects. It's like two people who look alike and therefore should be called by the same name. You know, so to call all of them as Faraday's Law seems to be blasphemous as far as I am concerned. I'm a little bit of a maverick when it comes to this. One, I would have rather liked to call this effect by one name and these two effects by another name, because the physics involved is different. The mathematics is the same. In each of these cases, agreed, the induced EMF would be measured by the rate of change of flux associated with the loop with time, but the physics for sure is different. There is, yes, in this case also, if there is a current, there must have been an electric field inside. All right, but then that electric field is not courtesy motional EMF in this case or the other, because the charges are at rest, right? And the second one, like I said, this minus sign is junk, is really junk. But, you know, it's a formality to put it all over the place so that you could be awarded some marks. See, two electrical elements that we have examined so far. Even before I do that, say there is a loop here, right? And there is magnetic field B like this. It's exposed to a magnetic field B like this. All right? And the loop is moved in this direction with a velocity v. The loop is moved in this direction with a velocity v. What would be the EMF generated in this loop? 0, because there is no flux associated. Realize the B going through the loop, perpendicular to the loop, is the flux lines going is 0. Cutting the loop is 0. So phi is 0. So, and it remains 0. EMF generated is 0. There would be no current in the loop, right? Suppose this is a loop and there are field lines going into the plane of the board. Field lines going into the plane of the board, and there is a loop like this. And there is a uniform B in this region. And the loop is moved with the velocity v to the right. What happens to the flux? No, there is flux, but there is no change of flux. Because B remains the same, the area of association remains the same, so flux remains constant. So rate of change of flux is 0. So EMF that is generated in this loop is 0. Current generated in this loop is 0. Induced EMF is 0. Induced current is going to be 0. Suppose this is a loop of area, say 2 meters square is the area of this loop, right? And it's exposed to a time varying magnetic field. It's exposed to a time varying magnetic field going into the plane of the board. Say the B going into the plane of the board is T square SI units. T squared SI units going into the plane of the board as a function of time. So the flux associated with the loop will change with time. What's the flux associated with the loop? Flux at any given instant of time is going to be A into B. A is constant. So then there is rate of change of flux associated with time. Rate of change of flux associated with time is going to be A into dB dt. A is 2, dB dt is 2t. So 40. So the EMF would be a function of time, a variable EMF. Variable EMF 40. 40 volts is generated. The direction of the induced EMF? Yes, very good. See, there are more field lines going into the plane of the board as a function of time. Do you realize that? Right? More and more field lines will go into the plane of the board. That means the direction of the induced EMF must oppose that change. It must throw some field lines out. So the direction of the induced EMF and the direction of the induced current must be such so that they throw some field lines out of the plane of the board, and that can happen if the current driven is like this. If the current driven is like this, anti-clockwise, so that some field lines can come out and they can partially mitigate the excessive field lines going into the plane of the board because of an increasing B. Right? Clear? Suppose there is a circular region which is exposed to a magnetic field which is not varying with position but is varying with time. Be a function of time. And let's say R is the radius of this loop. R is the radius of this loop. I now want to be able to compute the electric field. If B is a function of time, I want to be able to compute the electric field in this loop. I want to be able to compute the electric field in this loop. Realize that the electric field would all be tangential, isn't it? The electric field will all be tangential. I hope you realize that. It will be circumferential electric field generated, isn't it? Circumferential electric field generated because of symmetry. In this case, of course, let me change the direction. The direction would be not this. Now E dot dr, E dot dr, E dot dr along the loop will give me the EMF generated in the loop. So what's the EMF generated in the loop? E into 2 pi r. E into 2 pi r is the EMF generated in the loop, right? And by the way, these induced electric fields are not conservative in character. Unlike the electric fields that are produced out of static charges, these induced electric fields are not conservative in character. Write down, induced electric fields will not be conservative in character. Work done by an induced electric field in a closed path need not be zero. These are not, induced electric fields are not conservative in character. So E dot dr, E dot dr, right? That's the EMF generated. This must be the EMF generated, right? That must be equal to area, which is pi r squared into dB dt, right? Rate of change of flux with time. Area into dB dt, isn't it? Will give me change of flux. Flux is what? Flux is pi r squared into B. That's a flux. So d phi dt would be pi r squared into dB dt. Pi r squared into dB dt. So the electric field that is produced in the loop, tangential electric field, induced electric field. This is an induced electric field produced out of a time varying magnetic field. This is an induced electric field produced out of a time varying magnetic field, is given by R by 2 dB dt. This is a result we use often. Suppose this is a long infinite current carrying wire I. Long infinite current carrying wire I. And there is a square loop of side A by A. Square loop of side A by A. And initially at time t equal to 0, it's kept at a distance 2A from this current carrying wire. At a distance 2A from this current carrying wire. Now, there is a variable magnetic field to which this loop is exposed, because different strips on this in this loop are at different distances from the current carrying wire. Therefore, it's exposed to a variable magnetic field created by this current carrying wire. Now, as you keep moving away, the field decreases. So the flux penetrating this loop will decrease. So the direction of the induced EMF, the direction of the induced current must be such so that it can throw more field lines into the plane of the board, isn't it? dl cross r, there are field lines going into the plane of the board, isn't it? Because, and the number of field lines going into the plane of the board will decrease. Why? The flux will decrease. Why? Because B decreases. B decreases. Therefore, the direction of the induced current must be such so as to throw some more field lines into the plane of the board. More field lines could be thrown into the plane of the board if the current driven is like this, so that the B produced by the induced current could be into, right? Therefore, you would expect a current in this sense to be driven. If you used a minus d phi dt, I'll tell you it will not give you the direction of the induced current. As they say, the minus will give you the direction of the induced current. Induced EMF will not. All right, you will have to examine it from independent considerations. Now, if you at any given instant say at this instant, for example, I take a strip like this at a distance x, I take a strip of thickness dx, then there is flux associated with it. What's the flux associated? Now what's the B associated with this? Mu naught I by 2 pi x. The area of the strip is A into dx. Right? So the total flux associated with this is going to be sum of all of this, where x runs from 2a to 3a. Which is like mu naught I a by 2 pi log 3 by 2. That's the flux. Right? Now you can calculate the flux based on, let's say, this at a certain distance y, and let's say y changes with time. You would get the rate of change of flux with time, in the sense that at a certain instant, when this was at y, was at a distance y, then the flux associated with the loop, this is going to be, I would then take a strip of this kind, for example. I would take a strip of this kind at a distance x and of thickness dx. Then the same integral, except that x now runs from y to y plus a. To calculate the flux, I would take x now running from y to y plus a. That's the only difference, right? So the flux associated with the loop for this loop is going to be the same integral, mu naught I by 2 pi x a dx. X runs from y to y plus a. That's going to be the flux as a function of y. Right? That's going to be the flux as a function of y, which is like mu naught Ia by 2 pi log y plus a by y. Now, if someone gave you the fact that this was being moved with a constant velocity v equal to 1 meter per second, suppose that means dy dt is 1, dy dt is 1. The EMF generated in the loop is going to be given by d phi dt. D phi dt, that means d phi dy into dy dt will give you the EMF as a function of y, EMF as a function of y, where dy dt you can write as 1 meter per second, and d phi dy you can obtain by differentiating this. So you would get EMF generated in the loop as a function of y. As a function of y is what you'll get. Yes or no? Dy dt is 1. You would get EMF generated as a function of y. Clear? Now, and of course, the direction of the induced EMF, you realize, had to be in the sense that I showed, because it had to throw more field lines into the plane of the board to partially make up. You know, it's not able to make up for the loss of field lines or change of flux, but to a certain extent, it at least opposes that change. It opposes that change. Now, see, if there is a loop, and there is a current I flowing through the loop. Current I flowing through this loop, closed loop, and there is a current I flowing through this closed loop. Now this current I will generate magnetic field, see, going into the plane of the board. In this region, it will generate a magnetic field B going into the plane of the board. Yes or no? So there would be field lines going into the plane of the board. Right? There is flux associated with it. Right? The greater the value of I, the greater would be the magnetic field at various points. But however, the magnetic field at any point will be proportional to I because of Biot-Savart I dl cross R by R cube. Right? So, the magnetic field at any given point will be proportional to I. So, the flux in any given small area selected would be proportional to I. So, the total flux through this will be proportional to I, yes or no? The total flux, because of its own current, self current, because of its own current, self current will be proportional to I, the total flux. Right? The constant of proportionality that will appear here will depend on the geometry of this loop, and also will depend on the medium in which it is kept. Yes or no? Right? So the total flux associated will be some constant times I, where that constant will depend on two things: the geometry of this loop and the medium in which it is kept. Right? So it will be some constant L times I, where L is a constant whose value depends on two things: geometry for a given medium, and for different media it depends on the medium properties. Right? So this is a property of the loop. It's an electrical property. Now, here we have, in addition to two electrical properties that we have learned, one, resistance, two, capacitance, and now the third one, this property L, which is called inductance or self-inductance, coefficient of self-inductance. Sometimes they just call it inductance, sometimes they just call it self-inductance L, one way or the other. Coefficient of self-inductance. This is Webers, right? Flux in Webers, and this is current, and this L is measured in SI units, which is Henry. The unit of measurement of L is Henry. Flux is Weber, W-E-B-E-R, right? Tesla into meter squared. Tesla is B into area meter squared, that's Weber. And this is ampere. This L is referred to as Henry, the SI unit of L. Now, since L depends only on the geometry of the geometry and the medium, then if I maintain the geometry and if I maintain the medium, but I choose to change I, L remains constant, so flux changes. L will not change as long as I have maintained the geometry, and the medium, L is not going to change. But flux will change if I change I. Yes or no? So if flux changes, if I changes, there is change of flux with time. If I changes, then flux changes with time, which is L di dt. Right? But if the flux associated with the loop changes with time, there is going to be an induced EMF which would oppose that change. There is going to be an induced EMF that is going to oppose that change. This is the induced EMF, which will oppose this change. Yes or no? Suppose I is increasing with time, right? That means more field lines are going into the plane of the board, and the direction of the induced EMF, the direction of the driven current, induced current, must be such so as to oppose that change. Which means now, even though the original current I is like this, right? Even though the original current is like this, and if I is increased to a certain value, then the direction of the induced EMF would be like this. The induced current would be like this, so that it could partially dilute the increased I. So that it could partially dilute the increased I. And the induced EMF would be of this value. That means the induced EMF, behaves like a battery of this kind. The induced EMF in this case will behave a battery of this kind, which will oppose this current I, which will oppose this increase of current. This induced EMF will not oppose current, but will oppose change of current, because this I is increasing. It must oppose I so that it can negate to a small extent the changes that I is proposing in the flux associated with the loop. Clear? And this opposition to any electrical change, I is an electrical change, phi is an electrical change. So this epsa induced is an opposition to an electrical change. And do you realize, the greater the value of L, the greater the value of L, the greater would be the opposition to any change, right? Right? So this L is like what mass was in mechanics. It opposed change of motion, mass opposed change of motion. If a body was moving with constant velocity, two bodies, one of mass 5 kgs, the other one of mass 10 kgs, then which one would have greater inertia? Which one would resist change more, 5 kgs or 10 kgs? 10 kgs. Mass was a measure of mechanical inertia, right? Opposing mechanical changes, right? This L is a measure of what we refer to as an electrical inertia. This L is analogous to mass. What mass was in mechanics, L is in electricity. This is electrical inertia. We can therefore refer to this as an electrical inertia. This measures what's called an electrical inertia. An opposition to an electrical change. The electrical change is quantified by the flux associated with the loop. If that is changed, then this L will oppose that change by bringing in an induced EMF opposite to the direction of change. Yes or no? Clear? Makes sense to all of you, right? So far so good. So we looked at a property called inductance, essentially one that would oppose electrical change as in change of flux associated with it. The direction, like I said, could be obtained from Lenz's consideration. Now, a typical inductor element as used in electrical circuits is represented as follows. This is an inductor element, PQ. Having property L. Now, where is the flux? This is like coils of a solenoid, right? This is like turns of a solenoid, helical turns, right? That's the typical structure of an electrical inductor used in electrical circuits practically. Now, if there is a current I that goes from P to Q, then what that results in is a magnetic field in this loop. Yes or no? A magnetic field in this region is what this results in, right? Magnetic field produced in a solenoid. We've learned that, right? A magnetic field, so there are magnetic field lines going through it. And therefore, through this coil, through this solenoid coil, there is a magnetic flux associated with this structure. There is a magnetic flux associated with this structure. The magnetic flux associated with this will depend on I, will depend on geometry, will depend on the median, right? So the flux, like you already understand, will be, the flux through this would be like through the inductor element would be L, which is the coefficient of self-inductance of the inductor into the current I. That's going to be the flux associated with this loop, with this solenoidal structure, right? Now, as long as I is maintained constant, flux will be maintained constant, and like I said, this L will depend on the geometry and the median, right? Sometimes the medium here is just air, then it's called an air core inductor. Sometimes the medium here is a soft iron core, then it's called a soft iron core inductor. When you place a soft iron core inside the inductor, the value of L increases, is high. Not only that, if the soft iron core is inserted in this region and is movable, then we get a state of a variable inductor. We could end up getting a variable inductor. The air core inductor, the one that has air as the medium in this coil, is called an air conductor. It's called an air conductor and it has a relatively lower value of self-inductance. Now, this phi is L times I. Like I said, as long as I is maintained constant, phi would remain preserved and no issues with it. But the moment you propose to say increase I, the moment you propose to increase I, this change in I would be opposed, right? So then there would be an opposition to this increased I, and there is going to be an EMF which is generated. There is going to be an EMF which is generated. Imagine. Which is going to be d phi dt, which is like L di dt. That's going to be the EMF induced, that's going to be the EMF induced, which would oppose an increased current, and therefore the sense of the EMF, the sense of this EMF would be like this. Why? Why like this? Because it's going to oppose I. It would want to frustrate an increasing I, right? That's why this would be the polarity, right? That means the point where current enters would be connected to the positive terminal of the battery. The point where the current leaves would be connected to the negative terminal of the battery. So the element L then acts as a seat of EMF, which is L di dt, opposing the current I, right? Now, one thing. If you do not know whether I is increasing or decreasing, you still look upon the polarities this way only. In the sense, P will still be connected to the positive terminal, Q will still be connected to the negative terminal. This will still be replaced by this. In the sense, if di dt will then have its own sign. If I is increasing, di dt will be positive and this polarity will remain preserved. If I is decreasing, di dt will be negative and automatically the algebra will take care of it. You don't apply your brains to it because L di dt has its own brains. The brains will lie in di dt. Di dt will provide the sign that is required to the potential drop between P and Q. When I changes, we'll always look upon this as a potential drop from P to Q. We'll always look upon this as a potential drop from the point where the current enters to the point where the current leaves, and we'll represent the induced EMF with polarities as shown. Now whether it's going to be positive or negative would be contained in L di dt. Epsilon S will be L di dt, right? Clear? Now, typically, if this is an inductor element, it also has resistance. It also has resistance. Essentially, it has two properties then. It has an inductance L and it has a resistance R. Right? This is the equivalent between P and Q. That's a real inductor. That's a real inductor. And if a current I flows through it, then the drop across this part, now this part has zero resistance, this L actually has two components, L and R. The drop across this is going to be L di dt, the algebraic drop. It could be positive or negative based on whether I is increasing or I is decreasing. The drop across the resistance is going to be IR. So the net drop from P to Q is going to be, the net drop from P to Q is going to be drop across the inductor element L di dt plus IR. Yes or no? L di dt plus IR is going to be the net drop from P to Q. Now, in an inductor, if R is 0, if this is very small, negligible or 0, that means if R is 0, it's an ideal inductor. If R is 0, then we get what's called an ideal inductor. That's an ideal inductor. If that means an ideal inductor has no resistance in it, right? This is a real inductor. When R becomes 0, this is referred to as an ideal inductor. Clear? Now, realize that if this is an inductor element, connected between 2 points P and Q, then in order to build a current I in it, see, if there was no current in it, an initiation of current would be opposed. Now, to build a current I naught in it, essentially, let's say eventually I want to build a current I naught in it, right? From I equal to 0 to I equal to I naught, right? At an intermediate state, and of course, there is a battery connected to it which will build that current. There is going to be a battery connected to it which will build a current. And when I build a current I naught in it, very shortly we will look at growth of current in an inductor element, but that's another story. I just want to mention this fact to you right now. If a current I naught is built in it, there is going to be magnetic field lines associated with it for a certain I naught, and there would be magnetic field energy associated. There would be potential energy associated with this magnetic field. There is going to be potential energy associated with this magnetic field for a current I naught. Now, why is that the case? At some instant, let's say, during our build-up of current in this inductor element, from I equal to 0 to I equal to I naught, let's say at an intermediate state, the current was I. But I is changing with time, because I am building up a current, I am raising the bar. So then, at this instant, there is not just going to be I, there is going to be a rate of change of I with time. So there is going to be a di dt associated with this element. During our attempt to build up current in this element, there is also going to be a di dt associated with this element. So at this instant, there is going to be an opposition to di dt, which is given by this. There is going to be an induced EMF epsilon s, which is going to be L di dt. Right? Which means now, if you have to force this current I through this opposition, you would have to do work. If you have to force this current I through this opposition, this is the opposition. If you have to force this current I through this opposition, you would have to do some work. There is going to be power associated with it, right? You want to drive the current I at this instant. to oppose this, right? So if a current I has to be driven against an opposition V volts, then the power required to do so would be V into I, isn't it? The power required to do so would be V into I, right? So the power required to force I through this opposition is going to be, this is V, the potential hindrance, into I, right? So the power required at this instant is going to be epsa S into I. That's going to be the power required, which is like I into L di dt. These many watts. Who would give this power? The battery which is trying to drive a connect. The battery which is connected to PQ, which is trying to drive the current, will provide for this power. Yes or no? Which means now the energy required would be, in a small time dt, power remains practically the same number of watts. So power into dt would be the energy required, right? So the work done to drive through this opposition is going to be Li di dt into dt. Power into dt. Power into dt would give me Li di. Yes or no? Who will supply this energy? The battery will supply this energy. Where will this energy appear? Energy will appear as potential energy in the magnetic field. As potential energy in the magnetic field is where it's going to appear, right? The total work done to build a current from I equal to 0 to I equal to I naught will be this, which then, as you can readily see, turns out to be half L I naught squared. Half L I naught squared. That's the energy stored in the magnetic field in this coil, in this inductor element, when it has a current I naught associated with it. Clear? If inductor elements are there, they could be connected in various ways. There could be inductors in series, there could be inductors in parallel. So when I talk of inductors in series, this is an inductor element L1, this is an inductor element L2, and a current I flows from P to Q. And at this instant, there is a di dt associated with the current, right? And I want to be able to replace this. So in this case, L1 and L2 are said to be in series. L1 and L2 are said to be in series. Now this entire arrangement between P and Q could be replaced by one single inductor from P to Q, having a value L. For the same current I, the same di dt must appear, so that these two situations are equivalent. Right? Then, in order that they are equivalent, the drop from P to Q here must be the same as the drop from P to Q there for the same I and for the same di dt. Right? Now, what's the drop here? L1 di dt. What's the drop here? L2 di dt. What's the drop here? L di dt. So the total drop in this situation, L1 di dt plus L2 di dt must be the same as L di dt. Where L is the equivalent inductance for two inductors L1 and L2 in series, right? So the equivalent L then turns out to be L1 plus L2, right? Similarly, we could have had inductors in parallel. That is to say, this was one inductor element, say L1. This was another inductor element, say L2. And between P and Q, this arrangement is connected such that there is a current I coming at P and leaving at Q. And this I changes with time as di dt. Right? This I changing with time as di dt. And this I gets bifurcated into two currents. I1 across this and I2 across this. Right? The I then is I1 plus I2, Kirchhoff's law. So di dt is going to be d I1 dt plus d I2 dt. Right? Yes or no? This entire arrangement between P and Q, I want to replace between P and Q by a single equivalent inductor L, such that for the same current I and for the same di dt, the drop from P to Q here is the same as the drop from P to Q there. That's when these two arrangements are referred to as equivalent. Now, easy to see. What's the drop across this? L1 di 1 dt. What's the drop across this? L2 di 2 dt. I'm sorry, equal to. Isn't it? Because they are in parallel, the drop across this must be the same as drop across this. And both in turn must be equal to L di dt, the drop across this. Each equal to K say. Each equal to K say. Now in this di dt I replace by K by L. di1 dt as K by L1. di2 dt as K by L2, giving me the equivalent L as 1 by L equals 1 by L1 plus 1 by L2. That's the story of inductors in parallel. That's the story of inductors in parallel. Right? Do you all understand this? Clear?